she has been working since. And in our group, and in addition, she has been doing several research stays at different international institutions, such as the Center of Astrochemical Studies at the Max Planck Institute for Extraterrestrial Physics in Munich, and at the Joint ALMA Observatory in Chile. She is involved in several international collaborations and consortia, such as the ACES collaboration, which stands for the ALMA CMZ Exploration Survey, and I think she will talk about that a little bit today. And she is the coordinator of the chemistry and physical modeling working group for that collaboration. She's definitely one of the world experts in isotopic fractionation in interstellar medium, and that's what she's going to be talking about today. So thank you, Laura, and the floor is yours.
Sorry for the technical issues. So I hope this is the last version of the presentation, but if not, you will not understand it, so it's okay. So it's a very great pleasure for me to be here today presenting my research at CAB, where I work from 2020 now, so I'm very excited. Here is a list of some collaborators in this work. Here at CAB, there is Ascun, Jesus Martin Pintado, Victor Villa, Miguel Sanz Novo, as well as the entire group. And then, of course, I have many collaborators around the world, in Japan, in Chile, in Italy, Germany, the Netherlands. And all of the work that I will present is not only me. It's just to tell you that this is a very big collaboration among the observational side and the theoretical side. And today I'm going to talk about isotopic ratios, but not only, and their multiple aspects in astrophysics. Okay, so I'm going to guide you in several environments to tell you the importance about isotopic ratios and how we can use them. And I hope to convince you at the end of this seminar about their importance, also in astrophysics. And of course, I'm going to start with our solar system, what we know and what we can learn from it. So in this plot, I'm showing the 15n over 14n ratio as a function of D over H ratio, the deuterium over hydrogen ratio, for pristine solar system materials that is found in comets, interplanetary organic matters, some meteorites. And you can see that, let me see if I can, okay. All of these values are enriched in 15n and deuterium, with respect to the hydrogen and 14n, with respect to this value in yellow, which is the protosolar nebula value, meaning these isotopic ratios for the molecular cloud in which our sun was born. And then there was an enrichment of 15n and deuterium, so an alteration of these isotopic ratios during the sun formation. And we want to understand what are the processes that cause this enrichment in these less stable abundant isotopes. And to do this, one should go in star-forming regions. Now I'm going to give you a definition that I will use in the first part of this seminar. That is isotopic fractionation, which can be defined as the set of processes that distribute the less abundant stable isotopes of an element in different molecular species. And I will talk about hydrogen fractionation, that is deuterium over hydrogen ratio, and then carbon and nitrogen fractionation. In star formation, we usually use for carbon and nitrogen the reverse. That is, in the numerator, we put the 12C and 14N, and then in the denominator, the 13C and 15n, while for hydrogen is in the reverse. Okay, let's start with deuterium fractionation. The D over H ratio measured in comets, especially or in meteorites, especially from water, makes evidence that the ocean's waters come from these pristine solar system material. So this is one of the important measurements to try to study our origin to use isotopic ratios. But how this ratio changes in the star formation process. Here in this plot, there are summarized some of this is a very simplified plot, but there are many more measurement of this isotopic ratio in the interstellar medium. How it evolved the D over H ratio as measured from different molecular tracers, which are the different symbol or the different colors in different stages of the star formation, starting in the left from prestellar cores, protostars, and then more evolved stages like class 1, class 2 objects, which are already protoplanetary disks. At the very first stages of the star formation, these ratios tend to increase. The temperature decreases in these stages and the density is increased. When there is the birth of a protostar, the temperature increases and these ratios start to decrease. So there were many discussions in the past on why there are these changing in isotopic in the D over H ratios, but now, at least for the simple molecules, there is a common opinion on this from a theoretical side. So if we take into account chemical models, which took into account very even complicated chemical networks, this enrichment of the deuterium in the first phases of star formation can be explained introducing the so-called low temperature isotopic exchange reactions, which exchange one of the hydrogen of these three ions with the deuterium from the HD molecule, which together with H2 is one of the most abundant molecules, of course, in the interstellar molecular cloud. And then this deuterium is exchanged and these ions becomes enriched in deuterium. And they stay enriched if you have a very low temperature, like lower than 20 Kelvin, and also a very high density. Densities higher than 10 to the 4th and to the 5th centimeter to the -3. And they stay enriched because of their exothermicity. In fact, low and also some high mass starless cores, so the first stages of star formation, present temperature between 5 and 20 Kelvin. And then you have a very efficient four-dual reaction. You enrich this ion in deuterium, but the reverse reaction is not efficient because you will have a barrier given to the exothermicity. And of course, there is also an enrichment of atomic deuterium, which is absorbed on the grains, and this started an enrichment of deuterium for the species that form on the ice's surfaces, like methanol, for instance, which forms on grains. Okay, now let's move to nitrogen. Okay, this is a plot showing a lot of 49 over 59 ratios. The different colors are different molecular clouds or star-forming regions. For instance, in black, the low-mass prestellar cores. In blue, low-mass protostellar objects. We have the protoplanetary disks, sample of massive star-forming regions. And in the top part, you can see that they are also divided for the molecular tracers that have been used to derive the 49 over 59 ratios. And the horizontal lines represent the comet value, this very enriched M59 pristine solar system value, and in yellow, the protosolar nebula value. Here, there is not a trend for sure. So you see that it's completely a mess. It really depends on the molecule. There are some values that are similar to the comet's value, but then similar regions present completely different ratio. So what happens here? How we can explain this ratio? So this is still an open question. There are many ongoing works on this from the theoretical side, as well, of course, on the observational side. One of the things that one can think is, okay, for deuterium, this kind of low temperature isotopic exchange reaction works. So what if we use something similar for nitrogen? And of course, I'm not showing you some observation for carbon, but this is also similar for carbon. You can find different 12C over 13C ratio depending on the star-forming region or molecular cloud you are observing. So the first models started to introduce this kind of low temperature isotopic exchange reaction. Here I put some example for nitrogen. This is an exchange of the 14N from the molecular nitrogen with the 15N, and there is an enrichment of 15N for N2H+. But here you can see that the isothermicity is not so high. So this means that you have a very, very low temperature, but you still have some reverse reaction that is efficient. And indeed, if you look to this bottom part of the plot, which are some prediction from chemical models for the 49/59 ratios. This is the chemical evolutionary time, and here are 3 examples of molecules. Even you think there is some scatter, if you look to the y-axis, the values is not so different. So basically it stays the same as the initial condition you put in the model. So this kind of reaction cannot explain the observation of the different observed values for the 49/59 ratios. While for carbon, again, this is an example of a reaction that we recently used in one of our work. Again, here we have the different colors are different molecules and how they evolve with respect to time, to the chemical evolution time. And here you can see that the value can change indeed a lot. So for nitrogen, other processes have been proposed. I'm not going to tell you today anything about this, but just to tell you that if you are nearby an external, so you have nearby your molecular cloud a star that produces UV photons that arrive to your molecular clouds, or you have the protostar that is forming inside your molecular cloud, or again, you are in a protoplanetary disks, and then the external layer of the disk are affected by these far ultraviolet photons of the central stars. There is a modification of these 49/59 ratios, and some of them can really can reproduce the observations. So now we are really going to the direction to find a solution on this problem. So the take-home message here that I want you to stick in your mind for the rest of the seminar is that if you have high D over H ratios, they can trace the first phases of star formation, while 12C over 13C and 49/59 ratios are affected by different local physical conditions, which should take into account if you want really to understand what is happening. But I will come back to this later. So now let's focus to some regions in our galaxy, starting from the galactic center. Here in particular at CAB, in our group, we are really working hard on studies in the galactic center. The galactic center or central molecular zone, that is the inner 100 parsec of our galaxy, contains the 80% of the dense molecular gas in our galaxy. However, if you look to the recent star formation rate, it is 1 order of magnitude lower than that in the galactic disk. So what is happening? So the galactic center presents very extreme environmental conditions. For instance, some of them a very high level of turbulence. If you observe molecular clouds, the line width can reach up to 50 kilometers per second. And very high kinetic temperature from 50 even higher 100 Kelvin. All of this together with other conditions like extreme X-rays from supernova remnants and so on could prevent the star formation process. But we also know that this does not stop it entirely because there is some star formation ongoing, like the Sagittarius B2 and Sagittarius C hot cores, the Arches and the quintuplet young stellar object clusters, the BRIC, which is a region that has been proposed as a progenitor of a protocluster, as many other examples. Moreover, from an observational point of view, you should imagine that there are large column densities of this warm and turbulent gas that can make difficult to disentangle the presence of a denser and less turbulent component if it is present. So how we can identify and study these early evolutionary stages of the star formation if present? To try to tackle and to answer these questions, I'm going now to move to the Sagittarius B2 region. So if you have in the center Sagittarius A stars, you move basically to the eastern part and you will find Sagittarius B2. Here I'm showing the ALMA 3 millimeter continuum, the region, which is also, all of these are the site of ongoing star formation. So there are many hot cores with complex organic molecules. There are protostars inside some of them. If we move 55 arc seconds east from Sagittarius B2N, we found our favorite source in our group, which is G0693 minus 0.027, which I will call from now on G0693 for simplicity. And if we look to IRAM 30-meter observation of ethanol, which is this complex, at least for astrophysics, organic molecule, you see that there is a peak in the position of the source. And why this is happening? Why this region is molecular rich? Because this region is in the center of a cloud-cloud collision. So in the galactic center, there is a lot of turbulence, many clouds moving. And this region is in the center of this cloud-cloud collision, which produces shocks. These shocks spatter all of the molecules which in the past formed on the ices in the gas. And this is why we can observe them. And so we have, during the last 10 years we have performed this sensitive unbiased spectral survey towards this source with many radiotelescopes, the GBT in West Virginia, the JEBES and the IRAM 30-meter here in Spain, and the APES radiotelescope, obtaining frequency from 13 gigahertz up to 276 gigahertz. Reaching even sensitivity less than the millikelvin for the JEBES data, for example. And during the years, this allowed us to found a plethora of molecules, a lot of them for the first time in the interstellar medium. So you understand that this is a very special region. And in the last 5 years, 18 new interstellar molecules have been discovered, also of astrobiological interest, including oxygen, nitrogen, sulfur, and phosphorus, as well as carbon, of course, because they are organic molecules. But I'm not going to talk about this today because my research is mostly focused on isotopic ratios, as you already understood from the introduction of the seminar. And if we now take into account the part of this survey made with the IRAM and APES radiotelescope, we wanted to study the deuterium over hydrogen ratios of these 4 molecules, HCN, HNC, HCO+, and 2H+. And because of this unbiased spectral survey, we were lucky to cover many, 3 rotational transitions for each of the molecule used. This is very important because allows us to determine very well the physical properties of the molecular cloud as well as of the molecule that is emitting. And when we look to the spectra, we realized that we needed 2 line components to describe this region. So I zoom in here just to show you more in detail with the H15NC and H15, the 120 and the 322 rotational transition, as well for the 15N and H plus in the right. So first, we can use a turbulent component, which have a line width of 20 kilometers per second. And this is the typical one that we use in the central molecular zone or in this source in general. When I told you that we discover many of these complex organic molecules, this is the line component we use. It's just this one. But then, if you only use the green line, you really miss a part of the emission. And especially for the IJ transition, you could not explain at all the transition. And then we needed to add another component, less turbulent. So the line width is less than the half of the turbulent component, 9 kilometers per second, which is very clear indeed from these IJ transitions. Okay, then we have 4 molecules and 2 components. And for for all of this, we derive the D over H ratios. And in green, we have the broad turbulent component, so the typical of the source. And we have found D over H ratios for HCN and HNC higher than the cosmic value, while for HCO plus and N2H plus values that tend to be similar to this cosmic value. While if we go to the new narrow component, for all of the 4 molecules, we found ratios higher than the cosmic value. What this is telling us, okay, if we come back to these models that introduce these low temperature isotopic exchange reactions, so here I'm not going to detail, believe me, these ratios are consistent for the broad component, so the green one here, with a temperature at least higher than 70 Kelvin, which is still consistent with what we knew for the central molecular zone, and a high temperature. While for the narrow component, these ratios are consistent with temperature lower or equal than 30 Kelvin. So the first evidence of a very cold gas in the galactic center. We also perform a second analysis, so you do not have to read this, but basically, knowing the intensities of the line, the excitation temperature, we could derive, because we have more than one transition for each of the molecules, giving some hints for the kinetic temperatures thanks to the D over H ratios, we could give some constraint on the density of these two components, so the H2 density. For the turbulent component, the densities are around 10 to the third, 10 to the fourth centimeter to the -3. Again, what we already knew, what we expect. While for the other narrow component, the one that is also colder, densities could reach even value of 10 to the 6 centimeters to the -3. So this is telling us that we are in front of a possible cold and dense component. So maybe this is on the verge of star formation. To try to study more in detail this source, so we took into account now all of the unbiased spectral surveys, so all of the frequencies, and we use HC3N because we really cover a lot of transitions, as you can see here. And this is really helping us in giving more hints on the physical, so more constraints on the physical sides of these one, two, or multiple components. And in fact, if we zoom in two of these transitions, one is a low J component, which is also a low energy component, meaning in this case, I divided the transition in lower than 100 Kelvin and higher than 100 Kelvin. This is one of the low energy transition. This is why one of the high energy transition. For the low energy transition, still we need the two components, the green and the orange that I already shown to you in the previous slide. But if we go in the high energy, we needed a third component, so another one, which is still narrow as the other component. Indeed, their line width for HC3N are around 7-8 kilometers per second. And that only appears for these high energies. And you can also see that this other component is slightly shifted in velocity with respect to the other two, having a higher velocity. And we wanted also to know how they look like, because these observations are just single point observation. The only information you have is the spectra. You do not have any spatial information, so you do not see them in space. And then we go to SMA observation, coupled also with the single dish observation to retrieve for the extended emission, which can be lost from interferometers. Observation with the resolution of 4.4 arcsecond, which is at a distance of the source around 0.18 parsec. And we look to the HC3N 2423 transition, which is an high energy transition. So we expect to see both of the two narrow components. And in fact, if you see here in the right, there are these are the two components. So I have no time to go into detail here, but basically C2 and C3 are the two narrow components that I showed before in the spectrum. And C2 is this northern condensation, and C3 is western condensation in magenta. Also, in this case, we have performed this radiative transfer analysis, knowing the peak, the excitation temperature, and so on. And so we could constrain the density and the temperature for the three components. And knowing the source size of the two condensations, so C2 and C3, we could also give some hints on the mass. But focusing on the density, on the temperature, the C1 component, which is the broad turbulent component typical of the central molecular zone, again, we found value consistent, 2 times 10 to the first, 1 centimeter to the -3, and 140 Kelvin. For the condensation C2, which is this one in the northern part, we found a higher density, 510 to the 4, and the temperature of 30 Kelvin, consistent with what we found in the previous work with the D over H ratios and the other molecules. And for the new component. Here, the temperature is higher, which is expected because this is a component which appears only for very high transition, meaning higher than 100 Kelvin. And density in this case, which is even higher, 4 times 10 to the 5 centimeter to the minus 3. And we really think that this condensation have been formed because of the shock, because of the cloud-cloud collision, which compressed the gas and started to form these condensations. We also think that here, because of the resolution, we are not really seeing, but that there are multiple smaller condensation inside, and some of them, especially in C3, could even collapse. But we are now working on this with the new data. So let's hope to have more information in the future. So in summary, for this part of the talk, I have shown that our data in this G0693 source suggested the presence of a prestellar condensation that might be on the verge of the collapse for the first time in the galactic center. And one of the important things of the talk is that the first evidence have been found from the D over H ratio. So these ratios are very important. We can use now this ratio in the entire central molecular zone, hypothetically, to search for this kind of region, because this is special, but for sure this is not the only one. It's just the one for which we have many data at the moment. Okay, now let's move and change a little bit topic. So it's still isotopic ratios, but now let's move in the entire galactic disk. Isotopic ratios are also a good indicator of stellar nucleosynthesis. Indeed, the different elements and their isotopes are not formed in the same way during the star formation processes, depending on the star, on the masses, and so on. They can they can be primary product directly from helium, hydrogen, or secondary product from, so when you have the CNO cycle, which is efficient. Just to give you some example, for carbon, the 12 carbon is formed 50-50 from low and intermediate massive stars, while as a primary product, while the 13C is a primary product in low metallicity rotating massive stars and as an important secondary production in all kinds of stars. Nitrogen, again, another history. Both 49 and 59 as an important primary production in low metallicity massive stars. The 49 is also importantly produced in the CNO cycle in main sequence stars as a primary product in the convective envelope of asymptotic giant branch stars and as a secondary production in the hydrogen burning shells of red giants. And one thing that I want you to remember from now on is that the 15N as an important production have been found quite recently from the nova outbursts. And I'm going to tell you how this has been found. So what are the methods that have been used? All of these processes, not only for carbon and nitrogen, this is also the same for sulfur, oxygen, all of the elements you can imagine, are taken into account in galactic chemical evolution models, which study the stellar nucleosynthesis evolution in the galaxy as a function of the time, so from its formation as nowadays, and in space also. So you can really model the galaxy. And can give the initial condition of the isotopic ratio we currently observe in molecular clouds, because these molecular clouds have been, the elements have been driven by the evolution of the stellar nucleosynthesis. At the same time, the isotopic ratio we measure in molecular clouds can give a really important constraint to these galactic chemical evolution models, because there are many parameters that are not known or that cannot be constrained from the stars. So they really need the isotopic ratio we measure in this molecular cloud to put more constraint and to have more efficient results to know about the evolution of our galaxy. So this is very important. And that's it. No. La próxima. No sé si se para. Vete directamente. Yes. Sí. Okay. So now, the last part of this seminar, I'm going to talk about these two isotopic ratio, carbon and nitrogen. So, as I told you until now, these ratios are affected by the stellar nucleosynthesis as well as the isotopic fractionation in molecular clouds. So these physical conditions can really change this ratio that we measure. But from now on, let's forget these local effects that we know that are present and just focus on the stellar nucleosynthesis. I'm going for carbon to give you some one example in the literature, I think the main important one. So here we have the different colors, so the lines are the prediction of the Galactic Chemical Evolution model by Romano and collaborator 2017 from different prescriptions. So basically there are different stellar hills that can be used depending on the kind of stars, and they have different predictions. And they try to compare this prediction with the observations. In particular, in the left, we have the evolution of the 12C over 13C as a function of the time for the sun distance. So you take the sun distance and you see how it evolved with time, this ratio. And in the right, you take nowadays, so you stop at the last time, the simulation, and you see this how it evolved with the galactocentric distance. Okay, they compare with different observations, in particular for the molecular clouds we currently observed. You can, so they are located at different galactocentric distance. You can derive these ratios from many molecular species like CO, CO2, CN, and so on. And they compare. So basically, they found that in the early universe, the fast rotating massive stars are important, which are included only in these blackish models. While if we go to nowadays, they can reproduce this, let's say, slightly increasing trend better with this greenish model, using the carbon production hills from these authors. And I think that here is important is that in both cases, nova are not important to produce 13C. So 13C is produced in nova outbursts, but it's not as important to really define the different model that you want to use. If we go to, so in the past, so I was interested in studying this for nitrogen. And so I started to study many star-forming regions, around 100, located across the galaxy. The first part of the sample is a sample located in the inner galaxy, meaning from 2 up to 12 kiloparsec, and is a sample of around 87 sources. For all of these sources, I have derived the 49 over 59 ratio for HNC in the left and HCN in the right. And we have performed a linear regression fit, and we have found like a slightly increasing trend with the galactocentric distance. And we have also performed a parabolic analysis, and we have found this semi-parabola in red. So here, of course, I'm not giving to you the details. If you are interested, you can ask me. But the very interesting thing is that we decided at the time to compare with what was published from Galactic Chemical Evolution models, which here are these magenta solid lines, and have been taken from, again, Donatella Romano and collaborator 2017. And you can see that these models, taking into account, in this case, also nova, predict a linear trend up to a kiloparsec, so around the sun distance, because of the introduction of these nova outbursts, which are really efficient in producing D15N. If you do not have this nova, the trend is basically flattening. And then above 8 kiloparsec, a flattening trend because of the stellar hills that have been assumed for the formation of the 14N in low metallicity massive stars, which makes the production of nova less efficient, basically. And if you look to, in particular, the semi-parabola we have, the trend is reproduced, but not the absolute value. There are two main reasons I'm not going to detail here today because of this. One is from the side of the model, because as I told you at the beginning, there are many parameters that are uncertain and they have to assume in some way. One of them is the ejected mass in the form of 15N in a single nova outburst, which is, so there are many values in the literature from hydrodynamic simulation, and they have to assume one and can be different. And this can slightly change this absolute value. And the other thing is the chemical fractionation in this cloud. So it's from the observational side. As I told you, we just take these ratios and compare directly with what we think is just nucleosynthesis. But we know that there are chemical effects in this molecular cloud that we should really disentangle. And now me and my collaborator are really working hard with high resolution observation to try to really disentangle these, what is the chemical effects, removing it from this ratio that we measure, just leaving the value which should be the initial condition of the molecular cloud that we are observing. And this value should be used to compare with this nucleosynthesis model. And here is just until 12 kiloparsec. What about above 12 kiloparsec, meaning the outer galaxy? So 2 years ago, we started a campaign of observations with the IRAM 30 meter, the Jebes telescope, and also a triangular resolution with ALMA towards a sample of sources located in the outer galaxy from 12 up to almost 24 kiloparsec. This is a sample of 35 massive star-forming regions, and since I'm interested in isotopic ratios, of course, I've started to work on this. And for 14 out of 35 of these sources, we detected both H13CN and HC15N. So these molecular clouds are fainter with respect to the inner galaxy one, so it's more difficult to detect this kind of isotopologues because their emission is really, really faint, especially when the main isotopologues like HCN is faint, so it becomes difficult. This is why we obtain only for the for some of them, not for all of them. And we have derived these 14N over 15N ratios. I have added the new sources in the outer galaxy in the previous plot, which are the blue sources. And first you can see that if we just extrapolate the linear positive trend we found in the inner galaxy towards up the outer galaxy, we found that the outer galaxy sources are below the extrapolated inner galaxy trend. And the other interesting thing is that if we add these sources, we could continue this semi-parabola to the entire parabolic trend. So it's very consistent with what we found in the inner galaxy, and now we have this parabola. Then we started this nice collaboration with Donatella Romano because we told her, okay, now we have this observation in the outer galaxy, let's update and make new galactic chemical evolution model. And we performed these 4 models, taking into account different ranges of the ejected mass in a single nova outburst for the 15N, the 13C, and different masses for the white dwarf progenitors. So you can start from 1 solar masses or from 3 solar masses. And you can see that the green models are those that better reproduce the parabola, that are including nova with low mass white dwarf as the main 15N producer. And the decreasing trend in the outer galaxy is because there is a strong metal dependence on the 14N yields. Now Donatella and her collaborator are really trying hard to constrain better also from stars these yields in 14N to see if they can improve this shift from the observation. So even if this is within the errors of the parabola, still she thinks that it can be higher, this decrease. So it's not so deeply decreasing. Okay, so what we have learned from the Milky Way Isotopic ratios are key to constrain galactic chemical evolution models. However, do not forget the chemical processes in molecular cloud, which really we need to take into account from now on and really start this collaboration using observation, chemical models, including the more updated chemical network, all of the processes we think are affecting isotopic ratios, and galactic chemical evolution models, as well as updated stellar heals. So this is not my topic, but I know that there is also many ongoing work on the stellar side on this. And if we just come back a little bit to the 12C/13C ratio, in the left here, I put an updated galactocentric trend with many observations. All of the points are different sources, different molecules used to derive these ratios. And if we focus in the inner galaxy, where most of the points basically are, and if we compare with these four models we use for the 49/15 ratio, with the same models, we can also make prediction for carbon, oxygen, and so on. Again, the green model seems to be consistent in the inner galaxy, and the trend seems also to continue or slightly decrease in the outer galaxy, where, however, as you can see, in the outer galaxy, there are basically no constraints. So this is something that should also be done in the future. And look into the galactic center. So I will come back now in the last slide for the galactic center. There are ratios that goes from 10 up to 35, 40. And if we just extrapolate this increasing trend in the galactic disk to the galactic center, the value should be 10, while we see that the ratio seems to be even higher. So now the point is we need to study also the nucleosynthesis in the central molecular zone. We can be completely different with the prescription that we use for the galactic disk. And to do this, we need to constrain well the isotopic ratios in this environment, since there is this scatter of value. So what is the real value we should use? And thanks to this unbiased spectral survey, now I'm focusing to study all the isotopic ratios, so nitrogen. I'm starting from carbon, then nitrogen, sulfur, oxygen, and so on. Thanks to the fact that we cover a lot of transitions, we also have many double isotopologues, because we go so deep in sensitivity that we really see isotopologues, double isotopologues, which are really helpful for the optical thickness of the main isotopologue. Now I'm working on the 12C/13C ratio of HC3N and HC5N. I'm just going to show you these spectra. These are for the all the possible position of the 13C in HC3N. We have also the double isotopologues in this case, which are very faint, but we could detect them. There are not so many detection of this kind of molecules in the interstellar medium. And for this turbulent component, which is the one for which we can really constrain these isotopic ratios, because the narrow component in this spectra are very faint. So we are really within the noise. So it's really a bit more difficult. So meaning the one which is less dense and higher temperature one, we found a 12C/13C ratio of 37. For HC5N, again, we perform a similar thing for the main isotopologue and all the possible combination of the 13C, which are 5. And also from this molecule, we found a value of 35, consistent with the 37 of HC3N. What this means? If we go back to the plot here, this is in the higher part of this scatter of value. So we really think that now we need to constrain these isotopic ratios as well as possible, since now we can with this unbiased spectral survey. And spoiler, also from other molecules, the ratio is high. So it's like even above 40. And this ratio should be used then to be compared with the chemical evolution of the central molecular zone to study the nucleosynthesis processes that have been produced, that have occurred in the past. Many molecular species are needed because we are also using chemical models to see if there is a possibility that chemical effects are ongoing or not. or not. But for this turbulent high temperature component, we do not think that this is very important, but we still are doing this. And this is a shock region. So we are also performing a shock model to see if there is something remaining on the grains which could affect these isotopic ratios in what we are observing in the gas. But of course, this is only one region in the galactic center. So the ideal will be to have this very sensitive spectral survey in the entire central molecular zone. Impossible, at least now. So we can do something similar, but for simpler species in the entire central molecular zone now, thanks to the ACIS-ALMA large program, which is covering the inner 100 parsec of the central molecular zone with a resolution of 0.055 parsec. So we really cover, if you see in red, the entire central molecular zone in band 3. So this is an example of HNCO, the 423, which is a tracer of cloud. Also, we can go to core scale now, and this is a very important tracer of shock region. With this tracer, for example, we can search for other cloud as G0693, where to go and perform other spectral survey. But in this case, you are not blind. You really know where to go and then search for others, for example, other prestellar candidates. And so this is no. I'm finishing, so it's this last. Sopra, abajo, abajo. Ya, ahí. Sí, pon directamente el vídeo. Ahí, sí, a ver si funciona. No sé si funciona. Okay, so this is HNCO, the 423, looked at the different velocity, and you can see basically how the molecular emission is moving from there. That is the low velocity part, lower than 0. Then we go to Sagittarius A, there is the dust ridge, Sagittarius B2, and so on. So very nice data. And we are already starting publishing data. And as it has controlled at the beginning, we are leading the chemistry and physical modeling group. And these are the bands that we cover. We have dense gas tracers, shock, PDR, ionized gas, and hot core tracers. But of course, I'm interested in isotopes. And so we can really now do the 49/15 ratio, for example, as well as some 12C/13C ratio, maybe. Let's see how the opacity to deal with the opacity of HC15N, HN13C, HC3N. We have also some sulfur, the 134SO, which I had no time to talk today, but it's also another interesting element, and the methanol with the 18O. So this is my basically the last slide. I hope I convince you how isotopic ratios are important in astrophysics. They can be used in many ways, not only what I show to you today. So if you are interested, you can come and talk to me in my office. I am in the 38, the very last part of the corridor. And so thank you for having me today.
Thank you very much for this talk in which we have covered the whole galaxy, from the galactic center to the outer parts of the galaxy. So we move now to the questions part. Are there any questions? Yes?
Hi, Laura. Really nice talk. I have a couple of questions. First of all, have you confronted for instance, in the galactic center, there are a lot of red supergiants. And you can use the CO bands in the K band to measure the isotopic ratios, a very high resolution.
Yeah.
And those are very young stars. So have you compared whether the values you're getting in that region are consistent, or how much they differ with from stellar measurements?
Okay. Thank you for the tip. So for the moment, we I have not started to the nucleosynthesis part in the Galactic Center, but I can tell you that, so talking with Donatella Romano, but maybe you can say that I'm wrong. If you look to a specific star like red giants, they can give you an idea of the enrichment of the peculiar star, but not of how the nucleosynthesis during the time
Yeah, well,
have
in the
been
Galactic
affected.
Center, you have stars that are twice, I mean, they are 12 gigayears, and you have stars
Okay.
that are 10 million years old.
Okay,
And
so
then
yes.
you have stars with twice solar metallicity and 1/10 of solar. So you have
Yes.
everything there, but depending on the stars you're looking at, you should be getting as a function of time. The red giants are going to be much older, but the red supergiants, which are very bright, are going to be very young,
Okay.
and are giving you
Yes.
the current status of the metallicity at that region.
Thank
So
you.
that's one of the things you could. And the red supergiants are very bright, and the K band, the CO bands, with very high resolution, you can really separate the 13 and the 12 CO things. And then I have a second question concerning to the galactic studies you're doing. The galaxy is far from symmetric. I mean, so I was wondering if it's really a nature of nucleosynthesis in varying your isotopic ratios. Whether it was instead of using the radial, have you considered the azimuthal behavior, or plotting your things against metallicity rather than distance? Because there are going to be regions at the same radial distance with different metallicities, and that could give you a bias on your determinations.
Yeah, thank you for the question.
And that's for today.
So I think I have a plot. The answer of the first part of the question is yes, we plot against the basically the spiral arms, no? I don't see. Yes, here. So here in the right, so we plot the 49 over 59 ratio we measure. So I'm not talking about the models. The model, I think they're just radial models. So for this, maybe I should talk with Donatella if she's thinking to improving it on this side. But at least from the observational side, I can tell you that we do not find a trend. Still, if you assume there is just nucleosynthesis, as I told you, because there are also the chemical processes. And the second part, the metallicity, this is something I'm thinking in these days, because there is Pedro Umire that is doing something, so especially because many of these galactic chemical evolution model are not with respect to the galactostatic distance, but with the metallicity. So if you have an hint of how much it is the metallicity around your source, this could be something to do. However, it's not so easy to know the metallicity, because I was talking with Ithaskun and also discussing with Serena Viti about the metallicity in the Galactic Center, for instance. There are some measurements you also publish, but locally, so around our source, it can vary maybe, no? So I don't know, how do you think? So maybe we can discuss about you, all of these things. It's a very nice thing that we can discuss together. Thank you.
Thank you. Are there any other questions? I have one question. So you showed your preliminary results for the 12C, 13C ratio in the galactic center, and how that matches the galactic evolutionary models. But what happens with nitrogen?
Yeah, I can make another spoiler. So for nitrogen, oxygen, sulfur, all of these isotopic ratios in the galactic center at the end are very high with respect to just the extrapolation of what you found in the galactic disk. So if you just extrapolate, you will imagine or expect a value 10 for carbon, 20 for sulfur. For nitrogen should be around 200. But for nitrogen, indeed, it's like 700. So it's very high. So this is why we really need to make some chemical evolution. So what I think is that probably there are some primordial stars in the halo, which are influencing these isotopic ratios. Primordial stars should have higher elemental isotopic ratios, so which are like influencing the environment of the galactic center. But for this, so we really need to talk with some experts on this. And this is why I really like to use isotopic ratios, because allows me to make this collaboration with experts in many fields in astrophysics, so not only astrochemistry.
Okay. And if I may, so I have a second question. So do you think this kind of studies can be done in external galaxies?
Yeah, sorry, I forgot. Indeed, this was some part of the conclusion that were not in this version of the presentation, which was not the last, but you did it. So yes, this study, in particular in the central molecular zone, that now with this large program, we can really start to study in detail the isotopic ratios in the galactic center, will help to study these kind of processes in external galaxy and how external galaxies evolve, where this kind of resolution is not possible. So yes. This is also part of my project. Indeed, I am within the alchemy collaboration, which is study the chemistry of the central molecular zone of the starbus galaxy NGC 253. And I'm involved in the isotopic ratio studies in this. And so we are starting with this galaxy, which still you can resolve some giant molecular clouds in the center because it's quite nearby the Milky Way. But in principle, then you can have some prediction of galaxies in which you cannot really resolve.
Very exciting. Thank you. Are there any other, maybe some questions on Zoom?
There's
no questions? No? Okay. Then we can finish the talk today. Thank you very much, Laura. Thank you.